Now let's look at the more interesting case of two-branch recursion. And let's use another math example. In this case, let's calculate the Fibonacci numbers. Now the general formula to calculate the nth Fibonacci number is to take the n-1 Fibonacci number and the n-2 Fibonacci number and add them together, which gives us the nth Fibonacci number. But if we do it like this, we're going to go on forever if we try to calculate the fifth Fibonacci number, because when do we know we can stop? Well, we do have some base cases for us defined. The 0th Fibonacci number is 0. The first Fibonacci number is 1. So using this, what would the second Fibonacci number be? Well, it would be the n-1 Fibonacci number, which is 1, plus the n-2 Fibonacci number, which is 0. And we know that these are defined as a part of our base case. This is 1, so 1. This is 0, so plus 0. That means the second Fibonacci number is equal to 1. So now we have that. Then we can compute the third Fibonacci number, which we know is going to be n-1. That's 2 plus n-2. That's going to be the first Fibonacci number. So now we have the second Fibonacci number, which is 1. We have the first Fibonacci number, which is also 1. So this is equal to 1 plus 1. So therefore, the third Fibonacci number is 2. Now, the way I'm calculating it right now is very straightforward. I'm pretty much looping through these, and we could go as high as we want. We could now calculate the fourth, the fifth, the sixth Fibonacci number. But this is not recursion. The recursive solution for this problem is actually less efficient, but I still want to show it to you because it illustrates for us two-branch recursion. So let's say we want to calculate the fifth Fibonacci number. This is where our decision tree is going to get very useful. Maybe we can't immediately compute this, but we know this can be broken up into a couple sub-problems like n-1 and n-2. So to compute the fifth Fibonacci number, we can compute the n-1, which is 4, and n-2, which is 3. But for either of these branches, we still haven't reached the base case yet, which we know is 0 or 1. So let's continue down the left path. This can also be broken up into a couple sub-problems. Again, n-1 and n-2. So n-1 would be 3, n-2 would be the second Fibonacci number. For this, it's going to be n-1, which is the second Fibonacci number, and n-2, which is the first Fibonacci number. Now let's continue to draw this out. So the third Fibonacci number can be broken up into n-1, which is the second Fibonacci number, added with the first Fibonacci number. To get the second Fibonacci number, we can get the first Fibonacci number added with the 0th Fibonacci number. It's starting to get a little bit messy, but we're almost done. So over here, the second Fibonacci number, which we sort of just did over here, is also going to have 2 steps, which is the first Fibonacci number added with the 0th Fibonacci number. Now over here, do we also need to break this up into subproblems? No, because we finally reached our base case over here. So now to take a quick preview at the code, the base case we know is going to be either 0 or 1. So we could have an individual case for each of these. We could say if n, the input, is 0, then return 0, and if it's equal to 1, return 1. But we can condense that into a single if statement. If n is less than or equal to 1, that means if it's either 0 or 1, then return n, because when n is equal to 1, we're returning 1. When it's equal to 0, we're returning 0. So whatever it is, that's what we can return when it's less than or equal to 1. But for the recursive case, as we've been doing, we know we have to compute the n-1 and the n-2 Fibonacci number, and then when we have those, we're finally going to add them up and then return that integer value. But we're not quite done yet. We know that this here, the first Fibonacci number, it is 1. So that's what I'm going to put here. And actually, we've reached the base case with all of these, but there's just one branch left for us. So let's quickly complete that one, and then we can compute the result. So the second Fibonacci number we know is n-1, which is 1, plus n minus 2, which is 0 in this case. So adding these together will give us the second Fibonacci number. So now going down this path, let's say, for n minus 1, we're going to end up returning 1 in our code over here. For 0, we're going to end up returning 0. And then we're going to be back up here in our decision tree. For this, the code we're going to be at is this return code. We've computed n minus 1, which turned out to be 1. We computed n minus 2, which turned out to be 0. Now we're adding them together, 1 plus 0. So we're going to end up returning 1 from here. And this was also a base case. So recursively here, we would have executed this line of code and we would have ended up returning 1. You can see that it might not be easy to know what's going on just by looking at the code, especially when you get to 2-branch recursion and beyond that. That's why we draw out these decision trees, which make it relatively simple. So we know to compute the third Fibonacci number over here, we get the results of the 2 paths. We were first computing the second Fibonacci number, which turned out to be 1, and the first Fibonacci number, which turned out to be 1 as well. We add those together. So we add the return values from here, and then we return 2 from here. So now we're trying to compute the fourth Fibonacci number. First, we needed to compute the third Fibonacci number to do that. We did that here. Now we need to get the second Fibonacci number, and to get this, we get its subproblems, the first and the 0th Fibonacci number, which both are, well, this is 1, and then the 0th is 0. We add those together. That's going to be 1. So from here, we return 1. So to get the fourth Fibonacci number, we have 2, which is the third Fibonacci number, and 1, which is the second Fibonacci number. We add those together, and we return 3. Now, at this point, you're probably starting to get the idea. So finally, to get our original result, which is the fifth Fibonacci number, we needed to compute the fourth Fibonacci number. We did that. We have 3. And now we need to compute the third Fibonacci number. And to do that, we need to get the second and the first Fibonacci number. And to get the second Fibonacci number, we need to get the first and the 0th, which are going to be 1 and 0. Add those together. We get 1 as the second Fibonacci number. Add this and this together. We get 2 as the third Fibonacci number, and then add this and this, we get 5 to be the fifth Fibonacci number. It's gotten very messy here, but we did finally get our result. And again, this is definitely not the most efficient way to solve this problem. Earlier, we were doing it with a loop. So to get the nth Fibonacci number with the loop technique I was talking about, the time complexity would be big O of n. But here we've drawn it out recursively, and clearly this is not big O of n. So to analyze the time complexity of this recursive solution, looking at the code is not going to help us a ton. The picture is a lot easier to use, but it's going to require a bit of math. First, to get the fifth Fibonacci number, or just some general nth Fibonacci number, we have to break that up into 2 subproblems, right? And then those 2 subproblems have to be broken up into 2 more subproblems each. And then those subproblems might need to be broken up into 2 more subproblems, unless, of course, we've reached the base case, which for this one, we have reached the base case. But in general, for each of these, we might have to break it up into 2 more subproblems. Now, the fact that we have to break it up into 2 subproblems comes from the fact that we have 2 branches in our recursive tree. But in this recursive tree, how many times are we going to have to break it up into 2 steps? In other words, what is the height of this decision tree going to be? The height is basically how many levels does this tree have. You can see 1, 2, 3, 4, 5 levels. That makes sense because for the path where we have 5, then we have 4, and then to get that we have to go to 3, then to 2, and then to 1. That's what the longest path is going to be. So the number of layers in this decision tree is going to be n, where that's the nth Fibonacci that we're trying to compute. Now this is the part where I could get overly technical if I wanted to, but I want to try to keep it simple in terms of math. So in general for this, for us to get the number of Fibonacci values in the last level, theoretically with math, it would be we start with 1 and then we double every time. So it would in theory be 2 times 2 times 2, and the number of terms that we would have is equal to n. Roughly speaking, it's equal to n because that's the height of the tree, right? If we're taking this and then doubling it and then doubling it, the number of times we double it is going to be n, and that's the same as the input value. So to get the number of values in the last level is going to be roughly, let's say, 2 to the power of n. Now in this case, we can see that the last level only has 2. So in reality, this is actually an upper bound for the number of values we could have in the last level. It's not the precise value, it's an upper bound. But what we know about this last level is the same thing we talked about earlier in math. When you have a series like 1 and then 2 and then 4 and then 8 where you're doubling it every time, this is special in math. It's called the power series. It's always dominated by the last term. So 8 is going to be greater than or equal to all the previous ones combined. If we add a value 16, it's going to be greater than or equal to all the previous combined. So what I'm saying here is that this is an upper bound for the last level. That means it's also an upper bound for the total number of values in this decision tree. If you don't believe me, well, remember, we can multiply this by any constant. So we say, let's say our constant is 2. So 2 times 2 to the power of n is still, in terms of big O time complexity, equivalent to 2 to the power of n in terms of big O time complexity. Precisely, though, it would be n plus 1. But remember, we don't care about constants when they're multiplying or adding to variables. So 2 to the n plus 1 is equivalent to 2 to the n minus 1 as well, right? In terms of big O time complexity, all three of these are equivalent. So this is essentially a long explanation for saying that 2 to the power of n is how we can bound this in terms of big O time complexity. Even though this isn't the precise number of values in this decision tree that we drew, it's still a very good upper bound because remember, we don't care about constants like plus 1 or minus 1. And this idea of 2 to the power of n is something we're going to continue to see throughout the course. It all comes from that idea of math, from that idea of power series. 2 turns out to be a very special number for computer science and math.